Hello. How now can you hear me?
Yes.
Okay. Sorry for the technical issues.
Okay.
Now, welcome, Scarlett Gauthier and Michał Van Hooft. Is correct the pronunciation?
It's okay.
Okay. Thank you. Well, bueno. Now, would you mind if introduce your careers path?
Yeah, sure.
Okay.
So I'm working at the TU Delft, which is in the Netherlands, with Professor Stephanie Vayner, and I'm a member of the Quantum Internet Alliance. So my PhD has been in this direction, and I'm also a member of the architecture team, where we basically do like day-to-day monitoring of the progress of the Quantum Internet Alliance towards our goal of building a full-stack prototype quantum network.
Okay. You, Michał, can you introduce yourself or I introduce you?
No, I can introduce myself.
Okay.
I'm Michał van Hooft. I work as a simulation engineer, also at the TU Delft. And I'm also then, just as Scarlett, working on this Quantum Internet Alliance project. I'm mainly working on these simulation packages. Quite a lot of them I will introduce in my portion of this talk. Yeah.
Thank you, Michał. And the title of your talk is Towards a Global Quantum Internet Made in Europe, Q&A and your work. Please proceed. Thank you.
All right. Can you see my slides?
Yes, we can see.
Okay, great. So, yes, as an outline of this talk, we're going to start pretty high level and talk about quantum technologies just in a nutshell and the capabilities of them. Then I'll move on to discussing a quantum internet and what does this mean, a quantum internet. And then finally, we'll talk about the Quantum Internet Alliance, or QIA. So quantum technologies in a nutshell. You probably know that classical information can be represented as either a 0 or a 1. These bits, this is the classical way in which you can represent information, and this is the backbone of how modern computers work. In contrast, quantum information can be in a superposition state of both 0 and 1, and this is a unique property of quantum bits. But it's not the only unusual property that quantum bits have with respect to classical bits. They also have the property that they cannot be copied. This is coming from something called the no cloning theorem, and it's a useful tool that we can use to do interesting applications, also towards the quantum internet. There's also another special property that quantum bits have. They can share a special type of connection at a distance, and this type of connection is called entanglement. Entanglement has some very useful properties that we can use to do interesting applications. The first of these is that it's inherently private. So if two people, Alice and Bob, share an entangled pair, then their entangled pair basically can't be eavesdropped on, or somebody can't observe their entangled pair without disturbing it in some way. So they can notice if somebody tries to eavesdrop on their entangled state. Another unique property is that they can obtain maximum coordination from their entangled pair. So if Alice and Bob have this entangled pair and then they measure it, they'll obtain outcomes that match each other perfectly. So either they would both get an outcome of 1 or both an outcome of 0. And they can use this to do coordination without necessarily communicating in real time. The pillars of quantum technologies, basically the 3 different areas of quantum technologies we're developing today, are quantum computing, quantum computers being these devices that typically have very many qubits, and you do some kind of calculation on the quantum computer by making use of the many qubits available. There's quantum sensing. In general, quantum sensing tends to be that there's something like a single qubit device or a device with few qubits, or just one quantum device, and it interacts with some sort of environment and does some sensing of that environment. And finally, we have the quantum internet. And the purpose of the quantum internet is basically to connect many different quantum computers or quantum devices, and then be able to do unique applications with that quantum internet that you wouldn't be able to do with just the classical internet, and you also wouldn't be able to do with the classical internet plus quantum devices. So moving on to go a bit into more detail over what is this quantum internet that we're trying to build. So we can motivate further, why do you want to do quantum communication in the first place? And we hinted already that there are interesting applications of quantum communication. So there are applications in the domain of security and privacy. An example of this is the possibility of doing a secure quantum computation in the cloud. So some client would have a simple quantum device, and they can send it to a more powerful quantum device like a quantum computer, and they can have the quantum computer do their computation, but the quantum computer should not be able to learn anything about the calculation that they're doing. So this is secure quantum computing in the cloud, or blind quantum computing. Another application that's interesting is in the domain of accelerating networks. So here we can think about, for example, improved load balancing, and this is of existing networks. So think of something like the power grid, where you want to coordinate quickly the flow of power, and you can achieve applications in this direction. There are also novel features, so applications in the domain of proof of deletion or quantum money. And of course, most people have heard of the idea of scalable quantum computing, so making more powerful quantum computers by networking them together. Now, when we talk about the development of a quantum internet, we can turn to these functionally driven stages of a quantum internet, where basically we define the usefulness of a quantum internet together with its stage of development. So at the bottom of this stage of development, there are these trusted repeater networks. They're basically networks with quantum devices and maybe the ability to send quantum signals between devices that are close to each other, but you can't do any long distance quantum communication applications in such a network. Somewhere in the middle of this stack, you have entanglement generation-based networks or quantum memory-based networks. At that level of development, you can do some of the applications that I talked about on the previous slide. So for example, this blind quantum computing. And at the very top of this stage of development, you have a very powerful quantum network where basically you would have fault-tolerant quantum computers that are connected. And then you can really do any application of both a quantum computer or a quantum network. Now, there are efforts going on around the world to make this quantum internet a reality. And in Europe, one of the major efforts is coming from this Quantum Internet Alliance, which I'll spend more time on after. And there are also additional member state projects. In both the US and China, there are also many efforts underway. And right now, I'm speaking about efforts that are in the category of ground-based efforts. So what does this mean? This basically means efforts to build a quantum internet where the nodes of the internet are connected via a ground-based technology, so something like an optical fiber, which is already integrated into the telecom industry. In Europe, we have some startups that are becoming in the public sphere that are working towards this goal as well. So maybe WeLink, AQT, Qblocks, or Delph Networks. Maybe you've heard of some of these startups. In the US, there are some very large companies that are involved in trying to push forward the development of a quantum internet. So Amazon is involved, Cisco has efforts, IonQ also. We can turn also to space-based quantum networks, or basically quantum networks where a part of the quantum network is in space. So this would mean that you have quantum devices. They can either be on the ground, or you could have some in space on a satellite. And the links between quantum devices can go over a satellite link. So in Europe, working on this is the European Space Agency. In the US, NASA is working on this. And China has been somewhat at the frontier of demonstrations in the space domain for a long time, in that they've had a large focus on demonstrating satellite links for an application called quantum key distribution, where you basically make use of quantum devices to obtain a secure private key for communication. Now, where are we roughly in this development, and what are the next steps? Basically, in the last several years, and even going back a little bit further, there have been convincing demonstrations of trusted node networks. And some of these demonstrations have also been done in realistic settings, so fully deployed out in cities, for example. And this allows secure communication at short distances. roughly current development of a quantum internet, including real-world demonstrations, is at the stage of development where there has been increased connectivity in metropolitan areas. So there have been demonstrations of simple quantum networks that have a star-shaped topology, like the one illustrated here, where you have some central node and you have nodes around it in a star shape. And they've been able to do some applications such as quantum key distribution as well. This kind of figure here of the country, that's basically not a quantum figure, but it's just a figure which illustrates that as we get more developed, the infrastructure supporting these developments should also become more dense. And what is our long-term horizon? In the next 5 years or more, we're hoping to see early networks that have also increased functionality. So something more at this entanglement stage of development from our functional stages earlier. So you kind of imagine growing from a country scale, which is in the image on the left, to a continent scale, or this European scale on the image in the right. Now, I'll tell you more about the Quantum Internet Alliance, this large European effort to make our vision of entanglement for everyone a reality. So in the Quantum Internet Alliance, what we're trying to do is to build a quantum internet that enables quantum communication applications between any 2 points on Earth. That's our long-term goal. We have a backstory that basically starts in 2017, where 4 research institutions got together to try and strengthen the European efforts towards the development of a quantum internet. By 2018, Kia had grown to include 23 partners, so it's already much larger. And by 2022, we were an alliance of 43 partners, and we signed a grant agreement with the European Union to build a quantum internet made in Europe, which runs from 2022 to 2029. So I'll tell you more about that. But first, we will look at who is involved in the Quantum Internet Alliance. Basically, we're a team of global leaders in quantum technology with members that are from universities and institutions, so academic partners. We have members that are research and technology organizations, major industry players, quantum startups, some of which have kind of emerged as a consequence of Kia. And there are other institutions as well, like the Amsterdam Internet Exchange. We have a focus in diversity in the Quantum Internet Alliance on all types of quantum platforms that can contribute to making this quantum internet a reality. But we focus on certain platforms that are deemed really near-term feasible. Now, our goal is to make a quantum internet that's made in Europe. So Kia is developing a full-stack prototype network, and this network should validate all key subsystems, and it should simultaneously help to drive forward an innovative European quantum internet ecosystem that's capable of scaling all subsystems to world-leading European technology. So this last part is more about our innovation hub, which is illustrated on the right. Now, our first goal is this moonshot mission to build a full-stack prototype network. The prototype network should basically be consisting of 2 cities or metropolitan networks connected together over some long-distance backbone, where the backbone should have some distance of greater than 500 kilometers. This network should be a full-stack system, so it will be fully controllable and programmable. The nodes of the network should be data center compatible, so they shouldn't be sprawling optical table-wide setups. They should be these neat, packageable, transportable nodes. The quantum devices that make up these networks that can be accessed by users can be of 2 different types. So in each metropolitan network, you see illustrated photonic clients or processing nodes. Photonic clients are simple quantum devices that are meant to provide low-cost or easy access to users, versus processing nodes are more like simple quantum computers or advanced quantum computers they could be, so they have more advanced functionality. To validate this mission, we have 2 test programs. The first of which is teleportation above the classical limit. So this is basically about sending a quantum state from one side of the network to the other without converting it to some classical representation, and doing this in such a way that you can prove that it's basically non-classical behavior was observed. The other test program is blind quantum computation based. So I talked about this example a little bit earlier. And we are planning to validate blind quantum computation within a single metropolitan network. We have also a use case team, and the purpose of the use case team is to engage with early adopters. So basically getting companies and interested parties ready to adopt this technology and also co-developing with them new applications. Our second goal feeds into this. So we have this innovation hub, and the purpose of this is to become a world-leading European platform. So our team, which joins all relevant disciplines, all types of actors along the value chain, they work in leading European quantum network hardware platforms. They work to establish a world-leading European platform for quantum internet development. What is our latest news at Kia? We have new research and development. Here we see on the left, first illustrated, something about the long distance backbones that need to connect these two cities. So this is basically a validation of improved performance of the hardware that underlies these long distance backbones. So there have been demonstrated at the correct frequency to do this long distance quantum communication, this telecom wavelengths of light. We've demonstrated memory nodes which have a high rate that you're able to use them for, and you're able to use them very effectively. So supporting this long distance communication. There's also been developments at the metropolitan or long distance level. So we have demonstrated quantum network registers that can be reloaded basically very fast. So they can be used in either context, and they can be used both fast, but also very well. So the quantum states stay preserved very well when they are used on this node. Other exciting developments are that network nodes have gone into Iraq at two of the startups that we work with. So at Alpine Quantum Technologies, you can see here an ion trap-based network connected processor neatly packaged in Iraq. And similarly at WeLink, they have pioneered the Q drive, which is a quantum memory based on cold atomic ensembles. And what's really interesting is that by doing the hard engineering efforts to get these systems into these nice rack-mounted systems, instead of being these sprawling optical table setups, along the way during that development, this engineering has paid off, and the companies have seen better performance of the devices by these highly engineered solutions. So QDrive, for example, demonstrated a memory efficiency of greater than 90%. Other news is that we now have QNode OS, and QNode OS is the first system to program and execute quantum network applications on end nodes. So this is towards this effort of making a fully programmable quantum network that will be useful to users and more simple to interact with. Now, something that we wanted to tell you about is that we have this Quantum Internet Application Challenge, which runs from the 1st of November to the 21st of December 2025. And in this application challenge, you can pitch ideas, build prototypes, and help shape the real-world development of quantum use cases. If you're interested, you can scan this QR code to join or find more information about this. Basically, a kind of first prize of this challenge is an internship opportunity. And there will also be acknowledgements and engagement with runner-ups. So that concludes my part of the talk, and thank you.
Scarlett, I think there are some questions in the chat.
Okay.
If you like the question, we answer in the final of your presentation. Oh, now?
Sure, that's fine.
Okay.
So then I'll stop sharing, and Michał will start sharing.
Let me... Okay, can you share my screen? See my screen?
No.
Not yet. Yeah, wait. Yeah, no.
Now we see.
Yes, good. Okay. Well, I will be talking about the various quantum network simulators that are available, specifically those that have been developed here at TU Delft by our department QTech. So all of these packages, these are Python packages. All of these simulators over here are Python packages. And all of them are a quantum network simulator. And we didn't develop like 5 completely independent simulators. There is actually quite some relationship between them. Namely, every simulator tends to build up on the previous simulator, or at least use it to some extent. So why don't we just, for example, use the uppermost one, like the Quantum Network Explorer? Well, that's basically because every simulator has a little bit of a different target audience, a little bit of a different thing you can do with it. But the general, like, introductory overview is that in general there is a bit of a trade-off where the uppermost simulators are very easy to use, like very user-friendly, but they don't really allow you to design the network that you want. And then as we go down, and for example, NetSquid, it's a bit more work to get started, but it allows you the maximal ability of designing your network. So I will be introducing every of these simulators in a bit more detail, and we're gonna proceed this from going down from NetSquid up into the Quantum Network Explorer. So NetSquid as a user is sort of like you being handed a toolbox. And you then use this toolbox to really, in Python, create the simulation that you want. And then it gives you some components, specifically like you have these components that make up the network simulation, like nodes, ports, etc. Then, of course, we want to make it quantum. So we have the quantum simulation, like qubit circuits, quantum processors. And then this gets combined with the discrete event simulation, which sort of underpins this entire simulator. And since some of you may not be very familiar with the discrete event simulation, I will briefly introduce it. So in the discrete event simulation, we don't have like, we're not trying to simulate the time continuously, like we're not trying to approximate every time step. What we're doing instead is we have this event timeline. And on this event timeline, there are some events scheduled. Once we start our simulation, we might just have one single event, namely that Charlie is going to be emitting 2 qubits. One will be emitted to Alice and the other one to Bob. But then when processing this event, and when he actually does the action of, okay, I'm going to send this qubit, we're going to at that moment calculate, okay, how long is it going to take for this qubit to arrive at Alice? And we're going to find like, okay, it's going to take 2 seconds. So 2 seconds in the future, we will set a new event on the event timeline, namely that this qubit arrives at the Alice node. We do the same thing for Bob, which maybe is like 3 seconds into the future. Then once we've finished like this emission event, this initial event at Charlie, then control is being given back to the simulation engine. And the simulation engine will take a look at the event timeline and looks at what's the next earliest event that's, that we need to process. And then it will move the time to that event. So we'll jump from the Charlie event at the start to 2 seconds into the future. And then we start processing this event that this qubit arrives at Alice. During the processing, maybe new events get scheduled, like Alice measures that qubit and then sends that qubit along the message to Bob again. So that's the discrete event simulation. You just have events, that events get processed. During the processing of events, maybe new events get scheduled, and that loop keeps on going until there are no more events, and then you finished your simulation. So working with NetSquid is kind of like being handed a bag of Lego blocks. And then these blocks are, for example, things like node, quantum processor, connection, noise and loss model, and protocol. all of these blocks are really highly customizable. They're like Python classes. You can extend them like really drastically, create your own versions of all of them. And then once you have these blocks ready that you want to simulate, you then have to put them together into the network that you want to simulate and then run the simulation. So NetSquid really gives you a lot of flexibility. You can create almost any kind of quantum network that you want. The issue is, of course, you actually have to really spend some time on creating it entirely. The advantage is you're not the first person that's using NetSquid. NetSquid has been used for some time, and a lot of users have sort of given back to the community by creating these open source libraries that implement certain parts, certain functionalities using NetSquid. You can find them here on GitLab, Software QTech NetSquid snippets. So what can you expect in these snippets? Well, we have various snippets to model the different kinds of hardwares, like they come with their own quantum devices, their own loss and noise models for the specific hardware. So like we have snippets that specifically simulate trapped ion snippets, NV for nitrogen vacancy, and AE for atomic ensembles. In the NetSquid physical layer snippet, you can find some components, such as the linear optics Bell state measurement device. NetSquid Magic has some code to more efficiently simulate entanglement generation. And something like the entanglement tracker implements these protocols that track the entanglements in your system, but do so by classical communication. Then, of course, these snippets already give you quite a bit of head start, but it's still going to take you quite some time if you want to really assemble a functional network. Definitely once you're talking about more advanced networks, that takes a little bit of time and expertise. So that's where NetSquid NetBuilder comes in. Instead of you creating it, the entire network in Python, you instead have a YAML file. And in this YAML file, you just say, for example, okay, I have 2 nodes, I have like the Alice and Bob nodes, and we give them some kind of Q device. We specify the model that we want. We link them together with a quantum link and a classical link. Then the NetSquid NetBuilder, it will take this YAML file and give you a functional NetSquid network. Then it's still up to you to create the NetSquid programs that you want to run on that network. The NetSquid NetBuilder does have some restrictions. Namely, it's focusing on creating Kia prototype networks. This means that it only supports entanglement distribution networks, and that roughly there are 3 main types of network currently supported. You can create complete graphs, so just a bunch of nodes connected directly. These hub networks, where you have some central hub and all nodes connecting to it, or 2 hubs connected via a repeater chain. Then you can also still specify the various model and configurations for a lot of the components in this network, like what quantum device type you're using, what kind of entanglement generation model you're using between the nodes, what kind of scheduling protocol you're running on the hubs, and what kind of repeater control plane you want to run between the repeaters on the repeater chain. Then our next software is SquidASM. SquidASM is more built for simulating these quantum internet applications, because it allows you to simulate these NetQASM applications. So in NetQASM, that's a universal platform independent and extendable instruction set for quantum internet applications. Then SquidASM builds on top of this NetSquid net builder to implement sort of this control stack that would convert these netcasm applications and then actually execute these applications. So here on the right, you can see a short example of a little bit of the netcasm SDK. So SquidASM also notably is going to be used for the not the hackathon, the challenge that was mentioned before. I forgot the full name. Then the next one is Q&E. Q&E is also used for executing netcasm applications, or like the Q&E ADK. That's also for executing netcasm applications. It does support multiple backends. So if you choose to use the simulation backend, you're again using SquidASM. But it's also close to being able to simulate to use hardware as a backend. Then if you're using this hardware, you're able to run your applications on hardware we're providing here at TU Delft. Then the Q&E ADK also allows you to download and upload your applications to Q&E Call. The Q&E Call is the community application library. This is the website where you find a library of online created user applications. Over in this application library, you can see the explanation of the application. So if you click on the view details of an application card, you will get a more detailed explanation. And you're also able to run this application from your browser by clicking the Launch App, and then it will take you to this sort of not entirely interactive, but it will show you a more visual representation of what's going on in the network while you're running your application. Then one question may be like, okay, Q&E adds all of this stuff. Why should you ever use SquidASM instead of just always using Q&E ADK? Well, that's because there's a little bit of a difference in how you need to write your applications in order to be either compatible for hardware or in order to properly hook into the discrete event simulation. So what Q&E ADK does, it makes it more compatible for also running on hardware, but then it kind of loses this perfect hook into the discrete event simulation for the application part. And that will, it comes at some kind of penalty in how accurate your simulation is. The other part is that SquidASM, if you use it directly, you get a little bit more options regarding to setting up your network. Then, now that I've introduced all of them, I'll give you a little bit of an overview and sort of point to where you should use every simulation package for. So Quantum Network Explorer and SquidASM are both for application development, but then the Quantum Network Explorer excels more in the learning and outreach aspect because you have this community application library, so you can easily learn about a new application and also share yours. But then once you get more into the point where you've developed your application and you want to write a paper and now you want to really investigate things like your fidelity, your success rate, how quick is your application, then you should be using SquidASM to do this step. And if you're more in the process of designing a network or designing a network component and investigating how does this affect your network performance, then you have to use some kind of NetSquid version, and then it kind of depends on the exact type of network that you're simulating. So maybe in some cases you may be able to use NetSquid and then use a few of the snippets to get you a little bit faster where you want to go. Or maybe your network type actually fits neatly into what the net builder supports, and then you're like really more way ahead and you can get started way more quickly. So in order to learn any of them, in general, you can find some installation instructions for all of these packages. So for example, NetSquid, on the NetSquid page, you will find the NetSquid instructions. All of them will also have documentation available somewhere. So I'm not gonna list it for every one of them, but if you want to have the information, maybe do a print screen now. Notable is also that if you want to learn this application writing for either SquidASM and Q&E, we have a course available on this EDX platform. If you go there, you will find it's offering you the course with the certificate for $140. But if you choose the audit course option, you can still access all of the course content. You just don't get the certificate. With that, we come to the end and we can start answering your questions.
Thank you, Scarlett. Thank you, Michał. Your presentation is really interesting, and all your applications you development in the Europe Union. I have some question. Scarlett, how do you become interested in quantum networking, and what inspired your focus on the network control stack?
Sure. So I got interested in quantum networks in the beginning by basically having an internship opportunity in a group that was working to develop one of these types of quantum network nodes. So that kind of inspired my interest initially. And how did I carry forward into getting interested in the stack? That was somewhat of a roundabout route. So my background is actually in physics and mathematics, and I didn't have necessarily strong computer science background. But one thing I was really interested in was always communication and information. So I wanted to pursue something originally in a kind of more physics motivated direction. But the deeper I got into it, I understood that I was more interested in the design aspects of how do we make a functioning system that can do these interesting communication applications. So from that interest in a design aspects, I worked on more towards architectures for quantum networks, and so this was really what inspired my interest in the control stack. It was kind of this iterative process of learning more about how do these things function and wanting to contribute to making them a functional reality, and more from the computer science side than from the physics side in the end.
Thank you, Scarlett. We had another question for the participants. What are the main technical organization challenges in building a global quantum internet that is interoperable across Europe and beyond?
Yeah, so one of the main challenges in building a global quantum internet, like let's just say building any quantum network at all, there's a really big challenge in that comes from one of these unique properties of quantum states, and that's that they can't be copied. So in classical networks, one of the ways that we deal with being able to communicate very effectively is we amplify signals all the time. So we are able to copy data, and that allows you to amplify it as it traverses from its source to its destination. So this combats basically loss or noise that would corrupt the data or just make the data vanish as it transmits from source to destination. But you can't copy quantum states, so you need a different technique. And these techniques are these special nodes that we have in like a long distance backbone. You have something like called a quantum repeater, and this is doing a quantum version of this amplification of signal that you need to cover these long distances. But it's technically challenging. In order to have a functioning long distance link, you need to make entanglement at intermediate nodes along this long distance chain. You need to do something called an entanglement swap, which is basically a measurement that succeeds only probabilistically. So at every step of the process, you're incurring kind of some loss. So we want to combat this end-to-end loss. But even in this kind of technically demanding way of combating that loss, there are still losses introduced. So you're really stressed on the rate with which end-to-end communication can actually take place in these networks. And that's one of the fundamental challenges that basically everyone working in this domain is in some way trying to combat.
Thank you for that wonderful answer. We had another question for Sophia. Could you explain how the Quantum Network Explorer helps to developers and learners experiment with quantum network applications?
Maybe
That's
Michał.
my question. Yeah, so the Quantum Network Explorer is really useful for if you want to learn how one of these applications works. So you can go to this community application library, you can download existing applications, and also, as mentioned before, like these resources that get you up to speed to be able to write these applications also are quite good at sort of giving you the intuitive understanding. Like it will explain you the APR pairs, how you can use gates and stuff like this. And then the Quantum Network Explorer will, for various of these applications, will also just describe in detail how they are functioning and why they work and why they're useful.
Wonderful. We had another question for Brandon. How does AI balance research innovation with the need to deliver a practical, scalable application for users?
One way that we kind of balance the research-based innovation with making applications that are suitable for users and also directly getting user engagement is through the actions of this use case team. So the use case team basically has from the beginning worked together with some companies, for example, and together with the company, they focused on identifying a need or an area where there was a potential benefit for adopting a quantum technology as kind of seen by the company or as maybe presented to the company through some sort of an engagement. And then the use case team has been working with these companies basically to further develop unique applications that make use of quantum communication, but that are also targeted to a need or a perceived need from the company's side. So this is kind of how we work towards innovation that's already seeing like a practical adoption. And then another way that we work towards innovation that is really coming out of our research efforts is basically we have at many times we've had basically a group that was originally a subsystem group from within our effort. So we have these subsystems like these processing nodes or the long distance nodes, for example. One of these groups has spun off to become a startup where their technology was becoming mature enough for their subsystem that they saw an opportunity to become a startup. And so that's how we kind of further foster innovation from our research branch.
Thank you, Scarlett, for your answer. We have a question for Michał. What motivates you to specialize in simulation tools for quantum networks, and what do you find most rewarding in your work?
So I actually have a background in theoretical physics, but I've been sort of combining this with simulations. So I'm sort of like hybrid computer, software engineer and physicist. Then, yeah. What was the question again?
Okay. What motivates you to specialize in simulation tools for quantum networks,
Yes.
and what do you find most rewarding in your work?
Yeah, okay. So the specialization that really came from like I really already have like a very large quantum background. I really like working with quantum mechanics and stuff like this. And then yeah, just the job of being able to combine software engineering and physics, that's really ideal for me. And then for just daily what I like in my work, um, I both get to work a lot with scientists and like really support them with just this very interesting software development that I can make. And it's also something where you have like a lot of interaction with a lot of people. So you're sometimes as a software engineer, you just sort of disappear behind the screen and you never talk with anybody. And this is like a very nice, interact with a lot of people, support a lot of people, get to, add to the developments in like this breaking area, groundbreaking area.
Thank you. For both, what has been the most surprising or challenging problem you have to encounter it while developing quantum network simulations?
Can you repeat the question again?
Yes, what has been the most surprising or challenging problem you have been encountered while developing quantum network simulation?
Getting a good. Um, well, surprisingly, it's what I find the most interesting, or what's most complex, is the working actually on the software stack. It's actually like you would think that there is a lot of software, that there is like this is a lot of physics, but actually most of getting a quantum internet to work is actually getting all the protocols to work, and yeah, things like designing interfaces, stuff like this. This is surprisingly, uh, way more of a thing than you would expect. Um,
I would second Michal's answer. Basically, there's a lot more classical computer science and a lot more classical, just applied mathematics than you would expect.
Okay. Um, how you balance research, tool development, and collaboration across a large consortium like QIA?
I think one of the ways that we are able to work effectively together across such a large consortium is basically by having a clearly defined plan for what we are doing and for what each member of the collaboration is bringing to the plan. So we have, for example, this prototype network that we're trying to build, and it's really clearly identified what are the different subsystems of this network, who is responsible for the different subsystems, and also what are the interfaces between these subsystems. So that is something that's not always been clear from the beginning, especially actually Michał was sort of just talking about it. There are interfaces between subsystems that can take a lot of different forms also in the stack, and the correct identification of those interfaces and the support for those interfaces is an ongoing process. But we're able to work effectively by putting continuous effort towards that clear identification of the interfaces between all of the different subsystems and this kind of subdivision of responsibility, but then frequent communication also between the different members who are responsible for different tasks.
Thank you, Scarlett. Another question for young women and men in STEM from Latin America, what personal habits or mindset would you recommend for succeeding in cutting edge quantum research?
Yeah,
Mhm.
I think for me, one of the things that I find a really interesting way to get kind of more exposed to this field is indeed pursuing these kind of opportunities, such as this kind of application challenge, or these kind of coding hackathons we have sometimes, or internships in this field. Basically, these opportunities where you can interact with like trial versions of the technology, or with kind of opportunities to contribute to the development, or just to kind of learn more and dive deeper like this. I think that that's a really great way to both understand if you really enjoy kind of working in this field, enjoy more about it, and also meet other people who can kind of support this journey of going further in this direction. That would be my first kind of intuition in this direction.
I would second that.
Okay. Um, how far are we from a practical operational quantum internet, and what milestones should the community watch for?
I think it's easier to talk about the slightly shorter term. So if we talk about a global quantum internet, we won't see that developed overnight. There will be basically signs along the way of the development of this. And in particular, we'll see quantum networks that aren't global, but that cover some portion of the Earth, at increasing stages of development and functionality. So, for example, last year in the Netherlands, there was this quantum link demonstrated between Delft and The Hague, which was an entanglement-based link, where the nodes of that link were fully independent. And there was no kind of cheating used to do this entanglement between those two cities. So, for context, these cities are about 10 kilometers line of sight from each other. But in order to make this entangled link, actually, the quantum signals had to traverse more than 15 kilometers of optical fiber, which is just kind of randomly positioned under the roads. It wasn't made originally for quantum purposes, it was just there and repurposed for this. So that's an example of a key kind of milestone, is these real world deployments of networks which are not a quantum internet, but they're paving the way. We hope to make the prototype quantum network that we're trying to build in Kia another example of this, of a quantum network which will validate systems in types of real world settings, and showcase not only that these networks are possible to build, but also teach us lessons that can help us be ready to build even more advanced networks where increasingly they're in realistic situations, or we can open them up to, for example, outside users as well. So my advice for what should you watch for are basically these real world demonstrations that validate quantum networks in realistic settings.
Thank you. Uh, how do you see international collaborations, for example, between Europe and Latin America, accelerating the development of a quantum internet?
Well, I can definitely speak to, let's say, an aspect of international collaboration. I'm from Canada. And how did I end up at QTech in the first place? We have at QTech, there's a QTech scholarship, basically for master's students who want to do a master's thesis in quantum technologies. And so not only I, but also most of the other master students around me were international students, some of them from Latin America. And I see that as being a real enrichment of our community, where people have had opportunities to take part in these international collaborations, and we can bring kind of unique points of view, or just unique backgrounds. Everybody is educated in a different way in their home country. Just the educational curriculum tends to be a bit different. And so you have people with surprising amounts of depths in different areas, and that can make for a really rich community.
Thank you, Scarlett. Uh, what role could open source projects play in foresting? Sorry. What role could open source projects play in the fostering participation from students and researchers globally?
Mm, Open source projects are very basically just helpful to all researchers involved with basically their existence, especially if something's open source, you can tweak it for your needs much more easily and adapt it to what you actually want to do. And it also creates a really nice opportunity to be able to to be able to adopt something and build something on top of it to tailor it for your own purposes. Maybe Michał has something else to add, given all of our simulation tools.
Yeah, well, no, I would uh, pretty much second what you said. Like, open source really allows everybody to reuse these content and then build further tools. Because in the end, quite often we will be doing something which looks a little bit like somebody else has done. And it's also very nice to see, like, for example, these components being built up. And somebody else maybe like has a specialization in a different aspect. So let's say somebody really has designed a very good simulation of like a trapped ion approximation and gathered all the data. Well, then he can sort of share that in an open source project, and then maybe you're just more interested in network topology or routing of the network entanglement. But then you can just easily get to reuse all of that content that somebody else has made, and you can sort of enhance your research with a lot better content.
Thank you, Scarlett and Michał. Finally, one question. If you could share one inspiring vision for the global quantum internet, what would it be, and how could Latin America play a role in it?
So, an inspiring ambition for the global quantum internet, is that the first part of the question?
Sorry, yeah. If you could share one inspiring vision for the global quantum internet, what will it be, and how could Latin America play a role in it? Okay.
Okay. I think that for me, the most inspiring vision for a global quantum internet right now is basically the further development of applications that prove their real world worth. And this is something where basically anybody from any country can be involved in, because right now we have some applications of a quantum network defined. But some of these applications are not necessarily defined in very realistic settings, or they're described basically mathematically only, and they still need to be adapted to concrete advantage or to concrete settings that conform with the real world. So investigating new applications and using your creativity or using perceived needs that you see in the world to come up with applications or to adapt existing applications into these really real world beneficial settings. I think that's and also a world where this has been done successfully. That's what I see as a very interesting vision for a successful quantum internet future development.
Thank you, Scarlett, and thank you, Michał, for your excellent presentation and all your initiative you have. We now continue with the next speaker, and thank you really very much.